So we just did this room this week, and then for the rest of the term we're back into LT3, slightly larger room. Anyway, so back to lecture theatre 3 for the rest of this week. Just a heads up, the second class test will be held in this unit. We've got a collection of class tests coming up in units this term. Now, when you look on Moodle, it says a due date of 2nd of March, but that's the week ending the 2nd of March, Friday the 2nd of March. But the second class test will run it in a similar manner to the previous one, so we'll use the lecture slot, Wednesday lecture slot. So it'll be in the Wednesday of that week. I believe it's the 28th, that was one of those 20 months, the 28th of February, is that right? 28th of February, Wednesday. It's the Wednesday of that week. That's the Friday 2nd of March. It's the Wednesday of that week. It's at the end of February. Just a similar class test. So there won't be a multiple choice question test. It'll be more like a traditional Determinant test. But I'll give you more information about it in the coming weeks, show you some mock tests, and get you well prepared. Okay. So, coming back to our study of the derivative. So, summarizing what we've seen so far, we have the definition of the derivative. So the derivative is our quantity that is measuring the instantaneous rate of change of the function. We think of it graphically as as we explained last week, the slope of the tangent curve, the gradient of the tangent curve, the function of the tangent line to the graph of the function at a particular point. So the derivative of f at a, we can write it using this compact notation f prime of a, so we can use a prime attached. So prime is that superscript tick attached to the name of the function to indicate the process of differentiation. And how we defined it was using a limiting process. Limit as x approached a of this quantity, which was the f of x minus f of a. So it's the change in value of the function between the points x and a. That's what that quantity is, f of x minus f of a. But really, we should measure that relative to the change in value between x and a. If x is very far from a, we might expect the value of f of x to change a lot from f of a, even though the function f might really be slowly changing. So really, the difference in values needs to be judged relative to the difference in arguments. Okay? So that's what we call the relative change in value of function f between the points x and a. We think of as our fixed point. That's what we're going to measure the derivative at, and we take the limit as x approaches a of that quotient. Alternatively, just another way of writing it equivalently, you can also say that that's the limit k approaches 0, and you can write the fraction slightly differently. That's how I wrote it first. So I'm correcting myself. Sorry, correct myself again. F of a plus k minus f of a, and then the difference between the 2 points a and k. So this is the point a here. The difference between the 2 points a plus k and a is obviously this difference k. So here you're thinking of one fixed point a and one movable point x. Here you're thinking of one fixed point a and this offset k, which you're allowing to decrease to 0, to converge to 0. Okay? Exactly the same thing. And we saw last week some initial examples where we took some relatively simple functions, some powers of the variable x, and we were able to calculate their derivatives. But in order to develop our use of the derivative, we need to establish some properties of it. how the derivative interacts with the operations that we can do with functions. Once we have a good understanding of that, then we'll have a good understanding, or we'll be able, in principle, to get a good understanding of what the derivatives of compound functions are. Functions that are made up of simpler functions using the operations, the arithmetic operations, addition, adding functions, multiplying functions, forming quotients of functions, crucially as well, taking compositions of functions, applying one function after another. And each of those basic operations we can do with functions, we need an associated theorem about how the derivative behaves from those. So we develop now properties of the derivative. Properties about how differentiation process of taking the derivative of a function, how it interacts with operations amongst functions. Okay, so this is introduced in the notes as well. At the top of page 54. Now the nicest one, theorem 4.6, the nicest possible one, is about linearity. You'll be studying linearity in a lot of detail, or you already are really in your linear algebra part unit. Well, it's called linear algebra. It's the study of linear structures in vector spaces. And I don't know, have you come on to studying linear transformations yet? Well, if not, I think you will do fairly at some stage in this term. So linear transformations are the nice kind of functions you can have that act on vector spaces, that have vector spaces as their domains and codomains. And so the idea, the concept of linearity is widespread throughout mathematics. It's always extremely interesting when operations, transformations, or processes that you encounter, it's always extremely interesting when they are linear. Tends to mean that it gives you an insight and an ability to understand a lot about whatever the operation is. So in this context, what does linearity mean? Well, if you consider a pair of functions, f and g, and reals alpha and beta, sorry, let me call them G and H just to match the notation I've got for printing notes. Then consider the function f, which we form as a linear combination of G and H. So what a natural operations do is take two functions we have got and put them together in a linear combination to form a new function, f. If G and H are differentiable, they have derivatives, then what this theorem is asserting is that f is differentiable, and the derivative of f at a is the nicest possible thing it could be. It's going to be alpha times the derivative of g at a plus beta times the derivative of h at a. That is saying that the operation of differentiation is linear. Take the derivative of a linear combination of functions, you get exactly the same linear combination, meaning with coefficients alpha and beta, of the individual derivatives of the functions that have gone into making the linear combination. Okay, so a simpler way of presenting it is to leave out the coefficients alpha and beta, just say the derivative of a sum, g plus h, is the sum of the derivatives. And then some people might have a separate property about scalar multiples, about having a real constant multiplying a function and saying that the derivative of that is the same constant multiplying the derivative of g. But you can package them all up together if you have this. Now this seems like a very reasonable property, something we might have assumed, but it is true. But it is so important that it does deserve a proof, because not every you can easily put together meaningful, mathematically meaningful operations, transformations that you might do with functions, which would not be linear. So not every conceivable operation you might reasonably do to functions is linear. So we do need to be sure that when we suspect something is linear, that it actually is. So this can be proved. It can be proved using the definition. And the proof is really quite straightforward in that we just apply the definition and then apply what we know about limiting processes. Okay? So the derivative of f at the point A, well, it's the derivative of this function, alpha b plus beta h, the derivative of that at A. Now, I kind of argue that there's really only one reasonable thing to do at each step. What possible manipulations can we do at this step? Well, we've got the derivative of something evaluated at x. So really the only thing we can do is go to the definition. What does it mean to take a derivative of a certain function evaluated at a? Well, what it means is, we just go back to the definition, set it up. It means we're taking a limit as x approaches a minus a, and we have the function, whatever it is. So the function here is the linear combination, alpha g plus beta h evaluated at x. And we subtract the function, alpha g plus beta h evaluated at a. Okay. That's what the definition says it is. So that's the only kind of reasonable thing you can do there at that stage. And what can we do at this point? Well, okay, we might try and evaluate the limits at this point, but what we're looking at is all kind of fairly complicated, and all the g's and betas and alphas are all mixed up together. So it's not easy to say immediately what the limit of that expression is. Okay, quite complicated. But if you kind of glance at the results we're trying to prove, in the result that we're trying to prove, the g's and h's aren't mixed up. The g is all over here and it's being differentiated. The h is all over there and it's being differentiated. They're not bound together in a single kind of product term. They're just isolated on their own and differentiated. So that's kind of what we're working towards, but the state we have them at the moment, they're kind of wrapped up together. There's a g and a h over here and there's another g and a h over there. So the kind of natural inclination that's kind of pushing us, telling us what to do is, well, if we want to make this whole thing look like this, we can start to move towards that by separating out the g and the h. Gather all the g stuff together and gather all the h stuff together. Disentangle it. Okay? So we can do that by, so that's true just by the definition. There's not much we can do to the denominator at this stage, it's just x minus a. But that numerator, we can start expanding these brackets. Because what does it mean to evaluate this compound function of x? Well, what that means is to take alpha times g of x plus beta times h of x. And then expanding this one as well, it means to take minus alpha times g of a minus beta times h of a. That's just applying the definition of what it means to add functions together and do scalar multiples. And now you can start to see how you can start to gather stuff together. Say this, the limit as x approaches a, alpha g of x minus g of a, and a beta h of x minus h of a. Should probably have broken the fraction there. But at least that worked with the numerator. It kind of isolates all the g's together and isolates all the h together. You can start to see, a route through to the destination. Because we recognize these kind of things. The difference in value between g of x and g of a over x minus a. Difference in value between h of x minus h of a over x minus a. Those are exactly the quotients that occur in the definition of the derivatives of g, h. So rather than writing out loads and loads of lines, let's do a few further simplifying steps in one go. So I can certainly split that fraction, right? So I've got the numerator expressed as the sum of two quantities. So I can break that fraction apart into the sum of the two fractions. So then I'm taking a limit of a sum. Well, I can use the algebra of limits here for the limiting process. The limit of a sum is the sum of the individual limits. And those constants, alpha and beta, well, they're fixed constants. So the limit of alpha times something, I can take the alpha outside and say it's alpha times the limit of the other factor. And similarly with the beta. So we can perform a few manipulations here and say that this is alpha times the limit as x approaches a, g of x minus g of a for x minus a, all that, plus beta times the limit as x approaches a, h of x minus h, all over it. So there's a few things put together there. So the justifications for there was, mainly the algebra of limits there. Plus some algebra. The algebra needed to split apart the fraction into the sum of the two fractions. But mainly the algebra of limits there. Taking the limit of a linear combination of fractions and saying that's equal to the same linear combination of the limits of the individual fractions. Now we're ready, we can immediately apply the definition of the derivative once again, because it's sitting there right in front of our eyes. This limit is the derivative of g. This limit is the derivative of h. There's no more work to do other than to just quote the definition of the limit of the derivative of g, quote the definition of the derivative of h. So that's again by the definition of the derivative. And from beginning to the end there, we've got exactly the result we're trying to prove. The derivative of f, evaluated at the point a, is exactly the linear combination of the derivatives of the functions g and h. And f was that very same linear combination of the functions g and h. Alpha g was g. So we know now that the derivative is linear. Okay? We've got this proof of it here using an algebraic manipulation and the definition of the derivative, and the key thing is our knowledge about how the limiting process works. Okay? The limiting process. So really what we're seeing here is that the derivative inherits the linearity from the linearity of the limiting process. So that's proved as required. That equation there from beginning to end is exactly what we have. So, okay, any questions about that, Joy? Okay, so that's good. So now we know it's linear. Our next immediate impulse is to go for multiplication. Linear is all about this operation of addition of functions. We should immediately attempt to do the same thing for multiplication. So this is the product. But we inject a note of caution here. Not necessarily to take this down, but we might naively say, or hope, or expect. I mean, differentiation was linear. Maybe it's multiplicative. Maybe if f is the product of two functions, then maybe the derivative of f is equal to at a is equal to the derivative of g at a multiplied by the derivative h at a. Would seem entirely reasonable, or that maybe it's a good bet, because we just saw that it was linear. that the derivative of a sum was the sum of the limits. Maybe we might expect that the derivative of a product is the product of the derivatives. Okay, however, it's not true. Okay. So this is not true. Not true in general. Maybe for some specifically chosen or specifically arranged choices of G and H, that might be true, but it's not. That's only for coincidental reasons or trivial reasons. But typically, for functions G and H, it is not true that the derivative is equal to the product. The derivative of the product is not the product of the individual derivatives. So if that was true, if that property was true, then we would say the derivative is multiplicative. So if something does behave like that, it's called multiplicative. Some things are multiplicative. Some processes or operations are multiplicative. One interesting one you've encountered in linear algebra so far is what happens when you take the determinant of a product of two matrices? Have you encountered that? You familiar? How's that equation completed? You've done the determinant and properties of it. How is that equation completed? Det of A times the det of B. Exactly. So that's saying the determinant is multiplicative. The determinant of a product is the product of the determinants. So that's true, yes. That's true for every pair of matrices that it's possible to multiply against. So that's an interesting mathematical operation. It's in a different context, taking the determinant of a matrix, but that is multiplicative. Also, exponentiation. It's the fancy term for raising things to powers. Okay? Raising something to a power is multiplicative. If I take numbers A and B and cube them, I mean, what's one way you can develop that, to manipulate that? Cube A times B. Well, you can if you want. You can re-express that as A cubed times B cubed. So exponentiation of, let's say, real numbers at least, it is possible to raise other things to powers, another mathematical context. But for dealing with numerical quantities, then cubing a product is the product of the cubes. Of course, it's not linear. Run a bit of a diversion here. Classic mistake that I still see people making. They normally do it with squaring, but this is why people claim that. That this equals that, but no, certainly not true. Cube of a sum does include these two terms, but there's also lots of other terms as well, isn't there? There's what is it? 3 AB squared plus 3 A squared B. All right? Yeah. Yes. So that's correct. I haven't encountered people not thinking right and being a bit sloppy and saying, "Oh, that's equal to that." Yeah, no. So it's not linear. So these are. I'm just trying to emphasize here that these properties of linearity and multiplicativeness are very interesting properties, and we see all sorts of combinations of them in different mathematical contexts. You should always be on the lookout for them. So whenever you might meet a new operation or procedure, such as the determinant, and if there is a natural kind of an addition or multiplication type operation around, we can add and multiply matrices. It should always be asked. It's always an immediate good structural theoretical question to ask: is that process linear? Is that process multiplicative? Is the determinant linear? If you could add two matrices, You might take a bet or a punt or suggest maybe that's the determinant of A plus the determinant of B. It's not. So it's certainly not equal to the determinant of A plus the determinant of B. You can have situations where A and B, yeah, no, there just isn't any kind of, any such simple relationship between the determinant of a sum and the determinant of its sum. So you should always be on the lookout for linearity and multiplicity problem. So we're on the lookout for it here in our context of differentiation. So if f is a product of functions g and h, and g and h are differentiable, then f prime at a, which is equal to derivative of g times h at a. What is this? Well, it turns out that it's this. I mean, we could embark on a discovery of this, or we'll just put the result down and prove it. So we have something that you might be familiar with from your studies so far. So the product. So there is a relationship between the determinant of a product and the determinants of the individual factors. It's not this naive multiplicative one we might have suspected. It's this one here. Okay? So there is a sensible relationship between the determinant of a product and between the derivative of a product and the derivatives of the component function factors. Okay? But it's this kind of linear combination of the two. The linear combination of the two derivatives with the coefficients being the value of the other function, undifferentiated. It's a weird kind of mixture of multiplication and linear combinations going on. The derivative of a product is a linear combination of the derivatives of the factors, with coefficients being the values of the other function evaluated at the point we're taking the derivative. So this looks interesting. There's a pleasing kind of mixture and interaction between multiplication and linear combinations going on. So we can hopefully expect to prove this in a kind of a similar way, and dealing with products in kind of a similar, using similar ideas, principles that we have used previously. So, we launch into it with the definition. The definition says the derivative is the limit as x approaches a. The value of the product at x, difference between the value of the product at a, and all of this relative to the difference x minus a. Yeah. There it is. You can't hope to evaluate the limit yet. And looking at the destination, well, the destination, we've got individual bits evaluated at a, so we definitely do want to expand these brackets and evaluate the product function. So this is g of x, h of x, minus g of a, h of a. Now here, the route through to the conclusion is not so clear here as it was in the proof of the linearity case. It isn't the case that in the results the g's and h's are completely separated, because they do interact in both of the terms. So it's not that we're trying to divorce the g's away from the h's completely. But we do somehow want to isolate the difference, g of x minus g of a, because that's going to go into forming the derivative of g, And similarly, we want to isolate somehow the term h of x minus h of a, because that's going to go into producing that derivative of h of a. Okay, so we do want to separate them out somehow in the appropriate way. And so we just kind of go for it. It's maybe a little bit of trial and error, but we want to have something. We want to definitely see the difference g of x minus g of a appearing. I'm leaving a bit of space around these. And we also want to see the difference h of x minus h of a appearing. But how exactly they appear is up for grabs. So how can we, so I've got a kind of partially completed expression here. I want it to equal this. So what's, we start to think about one way we might do that. Well, so we start to look around and think, well, we definitely want to have minus g of a times h of a. We've got a minus g of a here. So one way to produce the minus g of a h of a term would be to stick in front there a h of a. If I put a coefficient h of a there, I would definitely get h of a times minus g of a. So I'd definitely get that piece there. Of course, I would also get this funny looking mixture h of a times g of x, which isn't up here. There is no h of a times g of x term up here. But that doesn't mean I've necessarily gone wrong here. I won't scrub that out. I'll leave that here because I notice that there's a h of x over here. And although this product generates h of a g of x, I can get rid of it again because, because I've got the minus h of a there. So I generate h of a g of x. I don't want it because it doesn't appear up there. But I can immediately get rid of it by placing a g of x as a coefficient there. So I get h of a minus g of a, which I want. I get h of a g of x, which I don't want. But this g of x times that minus h of a gets rid of it again. And it does introduce this g of x, h of x, which is exactly what I want. So this combination down here does equal that. But now there are many different ways we might have written, re-expressed this thing up here. There are many different ways we might have re-expressed it. But the thing that guided me was to first write down these two differences, right? Because those were the differences I needed to see that will ultimately produce the derivatives of g and the derivatives of h. When you further manipulate this limit, and eventually you're taking the limit of g of x minus g of a over x minus a. So this is looking good. This equation is true now. This numerator is the same as that numerator. Expressed differently, but it is the same. And I've just got a sum of two terms. So the natural thing there, I can split the fraction into the sum of the two fractions. So I can say here now this is a limit as x approaches a of the first fraction, which is h of a g of x minus g of a over x minus a. So there's the derivative of g bit, and here's the h of a bit. That's good. The other one is a little different, the other term, because it's not g of a at the front there, it's g of x. But the other part is the part I need to see to generate the derivative of h. So I just need to further manipulate this now using properties of the limiting process. This h of a is a constant. Because the limiting process is linear, that h of a can slide out to the front. That's it. The limit of a constant multiple of something is that constant multiple can move outside the limiting process and multiply the limit of the other factor. So using the linearity of the limiting process, You can manipulate the first term like that. Well, for this term, you see this g of x is not a constant. You can't just slide the g of x out to the front. It depends on x. It's a changing quantity under the limiting process because x is changing. The g of x is not a fixed value that can simply pop outside. So what we're seeing here is a limit of a product of two quantities, both of which depend on x. But we know the limiting process is multiplicative. The limit of a product is the product of the limits. When the two individual limits, the limits of the two individual factors, g of x and this fraction, when they exist. But now, in the inputs in all of this, we've assumed the functions g and h are differentiable. So that means the limit of this quantity does exist. We've assumed that g is differentiable at a, and part of that definition was that the function g had to be continuous at a. So it's the continuity of g we're also explicitly using. And so the fact that the limit as x approaches a of g of x is g of a. That's the continuity of it. So we use the fact that the limiting process is multiplicative, first of all. So the limit of this product is the product of the two limits. But then g is continuous. So the limit as x approaches a of g of x is g of a. And these two other limits here, they're exactly the derivatives of those functions by the definition. So we've got this constant h of a multiplying the derivative of g at a. The limit as x approaches a of g of x. Well, since g is continuous, that's g of a. And the limit as x approaches a of this quotient, that's exactly the derivative of h at a. And from beginning to end, that's exactly what we asked ourselves to prove. That's exactly the problem. That's as required. F of a, f prime of a, the derivative of f a is this linear combination of the derivatives of g and h. So that's our product. The differentiation is not multiplicative, but there is nevertheless a good systematic relationship between the derivative of a product, g times h, and the individual derivatives. It's not the product of them, it's a linear combination of them, using the values of the other function as the coefficients. Okay, so that's good. We've got linearity and product. We've dealt with addition and multiplication. So other things we have to deal with are quotients of functions, and then crucially, composition of functions. So still to do are quotients, like f over g. So that's the so-called quotient rule. And compositions. How to deal with the derivative of a function f after g. This isn't something called a composition rule, although it might have been called that, but the name attached to that is the chain rule. So remember, f after g is the composition of functions f and g. So if you evaluate f after g at x, it's the value f of g of x. So the functions are applied in composition sequence. G of x is applied first to the original argument x, and then f is evaluated on the result of g of x. It's an incredibly important operation. You can kind of get a taste for how fundamental it is. It's not just a scientific thing, it's a part of reality, because it is just basically doing one thing after another. And that could be anything. Living, dying, mixing things, breaking things apart, doing one thing after another, just everything in the basis of reality, combined operations in one way of looking at it. So it's an extremely important operation. Even though here we're only considering it amongst real value functions, but it is a kind of universal process, doing one thing after another. So we need a rule for that. Now, how are we going to tackle these? We're actually going to mix up the order a little bit, because thinking about quotients, see, a quotient f over g, you can kind of naturally think of that as f multiplied by 1 over g. So, you see, we've already gone to the trouble of proving a product rule, proving something about how derivatives of products behave. So a quotient isn't like some whole new kind of operation. It's got a strong relationship with multiplication. So we already know how to handle the derivative of a product of two things. We've already done that work, so we don't want to replicate too much work. So this other part, if only we could understand the derivative of 1 over something, then we could use that understanding, combine it with our understanding of multiplication, and then we'd know how to handle arbitrary quotients. And there's a nice way that we can express 1 over a function. It's a composition of r after g, where r of x is the reciprocal function. So r is not some general function represented by some letter f or g. It's a specific named function, the reciprocal function. Function that takes an argument and returns the fraction 1 over that argument. So an arbitrary quotient we can see as a combination of function f under multiplication with another function g after it's been composed with the reciprocal function r. So once we have the ability to handle the product rule, well, we've already proved the product rules, we know how to handle products of functions. But once we have the ability to handle compositions, which will be the chain rule. So we're going to prove the chain rule first, actually, before achieving the proof of the quotient rule. But once we have the proof of the chain rule, the only thing we're missing is the derivative of r over x. R of x, the derivative of the reciprocal. So once we have r prime of a equals whatever it is, once we know how to differentiate the reciprocal function, we'll be able to combine that with our knowledge of the product rule and the chain rule to say what the derivative of a quotient is. So in the time remaining, we can deal with this problem of what is the derivative of the reciprocal function. You've got to assume that a is non-zero. You don't want to be attempting to talk about this function at 0. It's undefined. But we can certainly apply the definition to find out what the derivative of this is at some non-zero point a. And you just apply the definition. It's r of x minus r of a over x minus a. R is the reciprocal function. So it's 1 over x minus 1 over a at x minus a. And that limit looks a little bit intimidating. I wouldn't say you could evaluate it explicitly directly now. You do need to do a bit of work here. See, both the numerator and the denominator are approaching 0. X minus a is approaching 0, and so is the numerator. So there's nothing we can do directly to evaluate the limit, so we need to work on it a bit. There's not much you can say about x minus a, but there is something natural we can do with the two fractions. We can combine them together as a single fraction. You got to remember how you add fractions. You put them over a common denominator, the x times a, and then you cross multiply the numerators in the right way. So to have 1 over x, we need to have a over x times a. And to have minus 1 over a, we need to have minus x over a. So it's this quantity a minus x. That's interesting, see, because a minus x is the negative of x minus a, so it's the same quantity above and below. So really this is, we've got the factor x times a on the bottom, we've got x minus a, and we've got minus x minus a at the top. So this troublesome 0 bit, it actually always cancels out, because it's there as a factor in the top, and it's there as a factor in the bottom. So remember, x is never reaches a in the limiting process, so this quantity is always a non-zero quantity, so it can be cancelled from the top and bottom of the fraction, leaving behind the quantity minus 1 over x times a. How does that behave as x approaches a? Well, this x bit is going to get closer and closer to a, so the whole thing is going to get closer and closer to minus 1 over a squared. So we do understand now exactly what the derivative of the reciprocal function is. The derivative of r of x is the function minus 1 over x squared. So that was the missing ingredient, so we understand what the derivative of r is. So now, the only thing we're missing really is the chain rule. So once we prove the chain rule, the other parts we need, the product rule, the derivative of the reciprocal function, we will have. And we'll be able to combine those, and that will prove the quotient. So tomorrow, we'll discuss the proof of the chain rule, and then straight away, we'll be able to just straight away combine all our rules, product rule, chain rule, derivative of the reciprocal, and that will give us our quotient. So we'll have a good, rigorous proof of that as well. Okay? So I'll see you again tomorrow at whatever time it is. Back up from JD, I believe.